Sir, may I ask you something? I'm confused about correlation and regression. Does correlation mean cause and effect? Or is it just a relationship?
That's a very good question, Anya. Correlation does not mean causation. Correlation only shows how two variables move together. It is the first step. Regression is used to study the internal relationship and prediction. Then, in research, we check construct validity and external validity.
Oh, I understand now. Correlation first, then regression.
Good. Now watch Dr. J.K. Sachdeva's video on correlation and regression.
Thank you, sir. We will watch the presentation and then actually work on R.
Welcome everyone to this session on correlation and regression analysis in R. In this tutorial, by Dr. J.K. Sachdeva, we learn how to measure and model relationships between variables using correlation and regression methods in R. You'll also learn how to interpret outputs and apply these techniques to your own data. Correlation and regression are closely related concepts. Correlation tells us how strongly two variables move together, while regression helps us predict one variable using the other. Both are essential in research and data analysis. Before starting, we'll prepare our dataset and store it on the desktop. Suppose we have data on height and weight for 20 individuals. We'll save it as a CSV file named correl_data.csv and load it into R using the read.csv command. In RStudio, we use the read.csv function to import our dataset. The head command lets us view the first few rows of the data and confirm that it has been loaded correctly. The correlation coefficient, usually represented by R, tells us both the direction and strength of a linear relationship. A value near +1 indicates a strong positive relationship, near -1 a strong -1. And near 0 indicates little or no linear relationship. We can calculate the correlation coefficient using the cor function in R. This will show how strongly height and weight are related. A positive value suggests that as height increases, weight also tends to increase. To test whether the correlation is statistically significant, we use the cor.test function. This function gives us the correlation coefficient, the t-statistic, and the p-value. If p 0.05, the relationship is statistically significant. A scatter plot visually represents the relationship between two variables. In R, the plot function helps us draw it. The pattern of points gives an immediate sense of the direction and strength of the relationship. Regression analysis extends correlation by allowing us to make predictions. The equation y equals a plus bx represents a straight line that best fits the data. The slope, b, tells how much y changes for a 1-unit change in x. We use the lm function in R to run a simple linear regression, where weight is predicted from height. The summary command displays the regression coefficients, the R-squared value, and the significance of the model. From the regression output, we focus on 4 important elements: the intercept, slope, R-squared value, and p-value. R-squared explains how much of the variation in the dependent variable is explained by the independent variable. We can visualize the fitted regression line on our scatter plot using the abline function. This shows how well the model fits the observed data. In multiple regression, we predict a dependent variable using more than one independent variable. For example, we can predict weight using both height and age. The lm function works the same way with multiple predictors. When reporting results, always include key statistics, the correlation coefficient, regression coefficients, R-squared, and p-values. This ensures your findings are clear, interpretable, and publication-ready. To summarize, correlation helps us understand the relationship between variables, while regression helps us predict one variable from another. Together, they form the foundation of statistical modeling in R. In the next session, we'll explore multiple regression and model diagnostics.
As discussed during our presentation, we are going to use the database which we have named it as correldata.csv, and it has got variables height, weight and age. There are 30 observations with height, weight and age. We are going to use this database for our correlation and regression analysis. I have already noted all the commands which I am going to use for our analysis. See down. It is saying R is a collaborative project with many contributors. Type contributors for more information and citation on how to cite R or R packages in publications. Type demo for some demos, help for online help, or help start for any HTML browser interface to help. Type Q to quit R. I'm just going to clear this because many things are there. The first thing is we are going to set the directory by saying set working directory C user Sachdeva desktop R databases. This you can also do it by session. In the session, you can set the working directory, choose directory, and I have already decided that I am going to use in my desktop R data files as my working directory. So we can set it like this, or we can simply write down set working directory in this run. So it is running set working directory. Please note all the slashes are backward slashes. And then we get the working directory. We get the working directory by run it working directory. It is telling me I am at desktop R databases. Now the next one, I am going to read the file Coral Data CSV, which is already there in our databases folder. So let us work on this data. Now this Coral data file will be saved in the variable data. I will run it. Okay, head data. I will see the few entries just to see whether the data is same or different. It is saying that height, weight, age, first 6 entries have been shown. Now, our first command is we have to run the correlation, core, between height and weight. Data $height and data $weight. Data's variable height and weight. We will run it. And it will show me down that there is a correlation 0.711258. Okay, let us try to make it a round comma 2. Let us run it by writing it here round core means correlation, data height, data weight up to 2 decimals. Let us run this up to 2 decimals. So it is rounded off up to 2 decimals because earlier we have seen this was showing 0.711258. Now it is showing up to 2 decimal. Now I'm going to clear it again. Correlation test. Whether the correlation is statistically significant or not. Let us run it. So it will show me the correlation. At the same time, it is telling me the T-stat is 5.3448, degree of freedom is 28, p-value is equal to 0.001 because it is written E-05. It means what? You have to put 4 zeros before 1. So it will be 0.00. Because the value is less than 0.05, we can say this correlation is statistically significant. Let us plot this. It will come on the right side. Plot will come on the right side. So we will say run. So it is the plotting here between height and weight, and blue color spots are there. It's already we have written that color should be blue. Now let us go for the linear regression. I am going to clear it. It is asking me yes, and I am going to clear this also. Now I am going to use this model, which is for my simple linear regression with two variables, weight and height. So I am going to run it. Now when I have said run, so everything that LM means regression, linear model. Data is our data. Now let us go for the summary. What is the summary of this model? Summary of this model is it is saying 96. T-stat is 0.384. Probability is 0.704. We can say p-value. Now this p-value is more than 0.05. So intercept is not statistically significant. But height is significant for weight. Height estimate is 0.6186. If height rises by 1 unit, the weight will rise by 0.6186 units. And it is statistically significant because p-value is less than 0.05. It is said significant value is 0. If there are 3 0, we can say it is 0.001. If there are two dots, if there are two stars, 0.01, that is 1%. Here we can say 0.1%. Here we can say 0.05% or 0.1%. So there are 3 stars. So we can say it is statistically significant at 0.1%. Now, further residuals, errors, 5.6 on 28 degrees freedom is given. Residual standard error, multiple R square is given this way, F is given this way. So model is statistically significant, but R square is 0.5059. What does it mean? 50.59% of the variances of weight, 50.59% variances are explained by height. Now let us see, plot it. Let us plot this again. Now in this plotting we are going to write the scatter plot line. So we will say run. When we are saying run, so red color line is there. This is your regression line, which you can say this is your red line. Now, if we want to take both the variables, that is height and age, to predict weight. Weight is your dependent variable. Height and age are independent variable. Data is this. So we will save it into multi-model. And then we will make the summary of that. We will say run. Now in this case, just see, I will in this case, I will little bit, little bit increase the font so that you may understand everything. Now let us see this. LM formula is weight depends upon height and age. Now residuals are given here, and your intercept is 0.5779, probability is 0.9739. This is not statistically significant, but height is statistically significant because it is showing 3 stars, that is significant at even 0.1%. And similarly, age is also statistically significant, and it is showing only at 5% level because it is showing 0.0187. P-value is 0.0187. So residual standard error is 5.138 at 27 degrees of freedom, and multiple R squared is 0.5989. It means 59.89% of your weight is explained by height and age. And the p-value is 0.000004.412 because it says E06. Thanks for watching this video. In our next video, we are going to discuss the multimodals. Thank you.